In my last video, I ended by asking the question, are there weaknesses in my blood test data? And I highlighted a total cholesterol of 133 as a potential problem. So in today's video, let's start off by investigating what's optimal for total cholesterol. And we can see that here. So starting with the hazard ratio for all-cause mortality on the y-axis, plotted against blood levels of cholesterol on the x. And this data is in 45 to 50-year-olds, 54-year-olds, or more specifically, 44 to 55-year-olds, which is what was included in the supplementary data for the paper. And if you're interested in looking at this paper, this and all of the papers in this video will be in the video's description. So note that this is more than 3.3 million subjects in this age range, and my chronological age is within this age range of 44 to 55, so it may be most relevant to me. So starting with the referent, which was defined as 220 to 229 for total cholesterol, and when putting my data into perspective, we can see that a total cholesterol of 133 milligrams per deciliter is associated with a more than twofold increased all-cause mortality risk. And superficially, this is bad news. So let's take a look at the aging data for a little bit more perspective. And note that low total cholesterol is found in youth, but also in older ages, which is what we can see here. So this is the larger study based on the study on the left, and this includes total cholesterol on the y-axis plotted against age of entry on the x. So this age range goes from 18 to 88 years. So what we can see for both men and women is that low total cholesterol is found in youth, somewhere in the 160 to 170 range, depending on if you're a man or a woman. And then total cholesterol peaks somewhere around 50 for both men and women, and after which we can see then an age-related decline, such that if we extrapolate further to about 100 years old or older, and I covered this in an earlier video, and if you missed that, it'll be in the right corner, we can see that relatively low total cholesterol can also be found in advanced age, including centenarians. So how can we know if low total cholesterol is reflective of youth or aging and increased all-cause mortality risk? So low total cholesterol within the context of other youthful biomarkers is associated with a decreased all-cause mortality risk. And that's what we can see here. So on the y-axis, we've got relative risk for all-cause mortality, and this is in people with total cholesterol less than 160 and with varying levels of albumin, ALB, and HDL cholesterol, HDL-C. And note that this data is in a very small study. It only included 393 people, so this may not be what actually ends up being the truth for people who have a relatively low total cholesterol. We'll need more studies in this area. But note, this study was published in 2001, and I haven't come across any other studies, including the study on the left, that adjusted their data for things like albumin, for example. So this is in 79-year-olds, and let's get into the data. So when compared with the hazard ratio of 1, when the brackets or 95% confidence interval is completely below 1, as indicated by the green arrows there, we have a significant effect, statistically significant effect. In contrast, when the 95% confidence interval overlaps with 1, as shown there, that effect is not statistically significant. So let's start off by defining the aged phenotype. And in this case, the referent actually ended up having higher all-cause mortality risk. So in that case, this was people that had a total cholesterol less than 160 and relatively low albumin and HDL, so less than 38 for albumin and less than 47 for HDL. And the reason that's the age phenotype is because I showed in the earlier slide that relatively low total cholesterol can be found in advanced age. So we've got total cholesterol less than 160, and then albumin and HDL decline during aging. So we see relatively lower albumin and HDL in people with advanced age. So combined, low total cholesterol, low albumin, low HDL, that's the aged phenotype. So what happens if we have relatively higher HDL within that context? And then, as I mentioned, we can see that the 95% confidence interval overlaps with 1. So this is not significantly different from the referent. So we can conclude that higher HDL, relatively higher HDL, doesn't impact all-cause mortality risk when we have relatively low total cholesterol and low albumin. What about when albumin is relatively high, as shown there? And now we have a significant effect, and I've defined this as the close to youthful phenotype because relatively low total cholesterol and relatively higher albumin are found in youth. And we can see that 32% decreased all-cause mortality risk as indicated by the green arrow in that group. But the best data of this bunch was for people that had the youthful phenotype of low total cholesterol and relatively high albumin and HDL. And note that again, those three would be expected to be found in people who are younger, chronologically younger, when compared with people of advanced age. So for that group, we can see that we had a 62% decreased all-cause mortality risk. So you can see the hazard ratio in the middle, 0.38. So to get the 62%, you do 1 minus 0.38 and you get 0.62, which would be 62%. A 62% reduction for all-cause mortality risk for people who had relatively low total cholesterol, but relatively high albumin and HDL cholesterol, when compared with people who had low total cholesterol, but the aged phenotype with low albumin and low HDL. And that's what we can see there. Relatively low total cholesterol, but relatively high albumin and HDL, those people have a reduced all-cause mortality risk. So before putting my data into perspective, there's another question that must be asked, which is how does this combination compare with higher total cholesterol for all-cause mortality risk? And they compared that in this same study. So we've got all-cause mortality risk on the y-axis plotted against years of follow-up. And in this case, they re-examined the 79-year-olds up to 6 years later. So now we have 3 cholesterol groups, but in this case, it's total cholesterol less than 160, but with the relatively youthful phenotype of higher albumin and higher HDL. And when comparing these 3 groups, including the 2 higher cholesterol groups of 161 to 239 and greater than 240, now there's no significant difference for all-cause mortality risk. So from this, we can conclude that low total cholesterol, but relatively high albumin and HDL, which again would be expected to be found in a youthful age or at a youthful chronological age, there was no all-cause mortality risk difference versus people who had higher total cholesterol. So to put my data into perspective for blood test number 5 in 2022, my albumin was 48 and HDL was 44, which is the close to the youthful phenotype. If my HDL was just a bit higher at 47, my data would be in the youthful phenotype. So based on this, accordingly, I'm not worried about total cholesterol of 133, but a relatively low DHEA sulfate is a weakness in my data. And we can see that data here. I measured DHEA sulfate on this same blood test where I calculated my biological age. And we can see that, first, we can see that my DHEA sulfate is 129 micrograms per deciliter. And just as a quick intro, DHEA sulfate is the most abundant circulating steroid in people. Now, a big part of my approach is going after the biggest fish. For example, albumin is the most abundant circulating protein. Red blood cells are one of the most abundant circulating cell types. So I think it makes the most sense to optimize the things that are the most abundant in blood first, while focusing on the things that are lesser abundant second. Now, if I only focused on the reference range, as shown on the right, of 61 to 442 micrograms per deciliter, I would miss this as a potential weakness in my data. So why do I think this is even a weakness in my data? First, DHEA sulfate levels decline during aging. And this is in a study of about 4,700 people. If anybody's come across larger studies, it looked thoroughly for larger studies, and I try to always show data for the largest studies, as they may represent the population averages more accurately relative to smaller studies. So for DHEA sulfate, we can see that it peaks around 20, and then afterwards it declines very steadily during aging. So putting my data into perspective of 429 micrograms per deciliter, which equals 3.5 micromoles per liter, we can see that I'm relatively low for my chronological age. And note that I'd be low even for younger ages. So that would be young for a 30-year-old. And even worse, this is what I'd expect to see someone who had an older chronological age. This may be common for people in their 60s, 70s, and 80s based on the aging-related plot. So this is only one data point, though. And as many of you may know, I have up to 39 blood tests since 2015. So is this an anomaly? I mean, is this representative of my actual DHEA sulfate level? So do I have earlier data for DHEA sulfate? And I do, but it's only from 2005. This isn't a commonly performed blood test. So for whatever reason, in 2005, I measured it twice over a 2-year span. And my average over those 2 tests was 300 micrograms per deciliter. And if we put that data on the age-related plot, we can see that it's there, and there's definitely been a decline for my DHEA sulfate levels during aging. Now, going further with DHEA sulfate, having a level at my current level is associated with an increased all-cause mortality risk, and we can see that here. So we've got the cumulative survival rate on the y-axis plotted against follow-up, and in this case, it was a relatively small study, but a very long study. You can see that there was a 27-year follow-up, which is very long for when compared with other studies. And the average age of these subjects was 51, which is pretty close to my chronological age, so it may be directly relevant. So what we can see is that the group that had the lowest DHEA sulfate levels, in this case 129 or less, had the worst survival rate when compared with people who had higher levels of DHEA sulfate, in this case, more than 200 micrograms per deciliter. So my DHEA sulfate seems to be a weakness in my data. Now, as I mentioned, is this one test representative of my actual DHEA sulfate level? So I blood test up to 8 times per year. Will this be representative of my year-to-year change for DHEA sulfate? So in earlier videos, I've mentioned that at-home blood testing may be the future of health optimization. And one reason for that is because you can collect a large amount of data in a short period of time. So with that in mind, I've used another at-home blood testing company to accumulate 12 blood tests using finger prick, in contrast with the venipuncture, which is how I obtained this DHEA sulfate level of 129. So I have 12 blood tests by finger prick within the last 2 months. Now, even with my rigorous testing schedule of up to 6 to 8 times per year, it would take me, a year and a half at most just by venipuncture to accumulate 12 blood tests. So at-home blood testing may be, as I mentioned, the future of health optimization. So to get those 12 blood tests, I used a company called Quantify, and as you can see, just with a screenshot from their website, their mission is to radically increase human lifespan. So anybody that's familiar with this channel, my motto is conquer aging or die trying. So I'm happy to use this product and to continue to use it in the future. And if you're interested in using it yourself, I'll have a discount link in the video's description. So what's my data for DHEA sulfate using finger prick? So we can see that here, and we can see that this is actually over a 7-week period, July 9th through August 27th. And again, 12 blood tests using the test Quantify from Quantify. And we can see over those 12 tests that my average DHEA sulfate level is 119.8 micrograms per deciliter. So that's pretty close and in the ballpark of 129. So from this, we can conclude that DHEA sulfate by finger prick may be as good as venipuncture for at least DHEA sulfate. So then the big question is, how will I increase DHEA sulfate? And if you remember, I started this video with cholesterol. So what does cholesterol have to do with DHEA sulfate? So DHEA sulfate is produced via cholesterol degradation, and we can see that here. So first, starting with cholesterol, and this would be a process that happens in the adrenal glands, which are located on top of the kidneys, and they happen at 3 different portions of the adrenal gland, as indicated by that black rectangle. So with cholesterol, after that's degraded into pregnenolone, pregnenolone is hydroxylated into 17-hydroxypregnenolone, which is then converted into DHEA, and then DHEA is sulfated into DHEA sulfated. So the formation of DHEA sulfated is just 4 enzymatic steps via the degradation of cholesterol. So now note that if relatively low DHEA sulfate is because of low total cholesterol, I would expect that cortisol and testosterone would also be low. And that's because 17-hydroxypregnenolone is converted via 2 enzymatic steps into cortisol, and DHEA is converted also by 2 enzymatic steps into testosterone. So what's my data? First, starting off with cortisol to see if that's true. And this blood test Quantify, the company Quantify, also includes cortisol and testosterone. They also have a female panel specific for some female hormones. So if you're interested in that, check it out. So for 12 blood tests using Quantify, my cortisol level is 12.5 micrograms per deciliter. So let's put that data into perspective by looking at the age-related changes for cortisol. And this again is from that study of about more than 4,700 to 4,800 people. So cortisol is a little bit different from DHEA sulfate. We can see a small increase for cortisol during aging. And putting my data into perspective, it doesn't look like it's low. It's somewhere in the midpoint of what you'd expect for someone of my chronological age. What about earlier data? Do I have earlier data, though, for cortisol? And for whatever reason, back in 2005, I measured it twice. And over those 2 tests, my average was 18.35 micrograms per deciliter. And when putting that data onto this plot, we can see that there, too, I've had a reduction for cortisol levels over the past 17 years. Now, whether 3 data points is actually representative of the true story, I'm going to have to measure this a lot more going forward in the future. So stay tuned for that. So we've got relatively low within my own data, DHEA sulfate and cortisol over the past 17 years, despite being on only a few blood tests. What about testosterone? So what's my data? So over those 12 blood tests, so at-home blood testing using the company Quantify, my testosterone level is 5.6 nanograms per deciliter. So let's put that into the aging plot as shown there. And the story for testosterone is similar to DHEA sulfate. It peaks around 20 and then declines during aging. And putting my data into perspective, although it's not low based on the overall population, you can see I'm somewhere towards the higher end of the age range for a 50-year-old. I do have earlier data, but only one test in 2005. And we can see that I've also experienced a decline for testosterone. Now, what were my levels of cortisol and testosterone optimal in 2005? I don't know. But again, I'm going to continue to measure these biomarkers and see how the story plays out with the specific focus on optimizing DHEA sulfate. So just as a brief summary, we can see that I've had within my own data age-related declines for these three biomarkers for DHEA sulfate, cortisol, and testosterone. So when considering that these hormones are produced via cholesterol, in my opinion, the first step would be to increase blood levels of cholesterol. So how can I do that? What's the best way to do that? And for those who don't know, I've tracked my diet every day with a food scale since 2015. So I have dietary data that corresponds to each blood test up to 39 blood tests. So I can see within my own data what the best way may be to optimize blood levels of cholesterol. And for me, that may be by increasing dietary cholesterol. Now, I know that I've heard people saying that dietary cholesterol doesn't raise blood cholesterol, but we can see very clearly in my data that a strong correlation with a correlation coefficient of 0.7 and a significant p-value, that dietary cholesterol in my case may raise my total blood cholesterol. Now, just for reference, for blood test number 5 in 2022, we can see that my average daily dietary cholesterol intake was 24 milligrams per day, and that is in conjunction with a blood cholesterol of 133 milligrams per deciliter. So when considering this correlation for dietary cholesterol with blood cholesterol, it would seem that with the goal of increasing DHEA sulfate, I can easily maximize dietary cholesterol intake, which may optimize blood level or increase blood levels of cholesterol. But will I improve one biomarker, DHEA sulfate, and make others worse? So let's check that out. So here we're going to see correlations for dietary cholesterol intake with big picture biomarkers. And for those who may not have seen this analysis on my channel, I'll just run through it real quick. These big picture biomarkers represent many biomarkers of organ and systemic health, including glucose, which should be in any anti-aging approach, a marker of methylation, including homocysteine, 3 markers of kidney function, 3 markers of liver function, all the major lipoproteins, HDL, LDL, VLDL, and lipoprotein A, immune-related cells, and the proteins, including globulins, red blood cell related measures, a marker of inflammation, high sensitivity C-reactive protein, and overall biological age scores indicated by Levine's PhenoAge and aging.ai. So we've also got some other information on this table. In this table, the little n next to each blood test is how many blood tests that I have data for it. So for example, for glucose, I have 37 blood tests since 2015. The R at the top left is the correlation coefficient, and the p-value at the right. On the right is the measure of statistical significance, with less than 0.05 being statistically significant. So what's significantly correlated or how does dietary cholesterol significantly correlate with these big picture biomarkers? So a higher dietary cholesterol intake in my data is significantly correlated with higher blood urea nitrogen, BUN, higher alkaline phosphatase, higher LDL, higher levels of neutrophils, a lower lymphocyte percentage, higher levels of monocytes, higher platelets, higher levels of red blood cells, and that's it. So we've got 8 significant correlations within my own data for dietary cholesterol with other big picture biomarkers. And note that once I've got enough data for DHEA sulfate, I'm going to include that on this list as a big picture biomarker. So we'll expand the list by at least 1. So then the next step is to address, are these significant correlations going in the right or wrong direction in terms of aging and or all-cause mortality risk? Now, I've covered biomarker directionality in terms of aging and all-cause mortality risk in other videos, but just as a quick review, for example, blood urea nitrogen, alkaline phosphatase, neutrophils, and monocytes increase during aging, so that we have positive correlations with dietary cholesterol suggests that these are going in the wrong direction. So I've given them red arrows. If anyone's got questions on the other biomarkers and why I've given them red arrows going in the wrong direction, just leave a comment and I'll be happy to address that. So now that we've got a net score of -8, so 8 red arrows, 8 correlations going in the wrong direction in terms of aging and all-cause mortality risk, what do we do with that information? So if the net score was positive, I would eat above my average intake for total cholesterol, for dietary cholesterol. If the net score was 0, I would eat my average intake since 2015 for cholesterol. And in this case, because the net score is negative, that suggests that I should eat below my average intake for dietary cholesterol. Now, since 2015, my average dietary cholesterol intake is 126.4 milligrams per day. Now, just for reference, we can see that for this most recent test a couple weeks ago, it was 24 milligrams per day. So to stay within my own rules, to eat below my average, I can go from 24 up to 126 for dietary cholesterol in order to follow the correlations. And I think that following the correlations as much as possible leads to the best overall biomarker data. So my current cholesterol intake, with the aim of increasing it but staying below my average intake since 2015, is now 91.5 milligrams per day of dietary cholesterol. I've done that by adding a couple of eggs per week while still sticking to the macros and micros that have resulted in this biological age profile that is somewhere in the 15 to 20 year younger range when using Levine's and aging.ai tests. So then the big question is, can going from 24 to somewhere around 90 milligrams per day for dietary cholesterol, will that increase DHEA sulfate but not mess up the other biomarkers? So stay tuned for that in future videos. We'll address that data. All right, that's all for now. If you're interested in more about my attempts to biohack aging, check us out on Patreon. And before you go, we've got a bunch of discount links, including at-home blood testing using Quantify. And note that these are all companies that I use and will continue to use in the future. So if you're interested in using them yourselves, feel free to use these discounts. If you want to test your epigenetic age using True Diagnostic, I've got a discount code for that in the video's description. Oral microbiome composition, my second test results should be coming any day now, so I'll have an update video coming sooner rather than later for that. If you want to track your diet using Chronometer, which is what I use, we'll have a discount code for that in the video's description. And last but not least, if you'd like to support the channel, you can do that with the website Buy Me a Coffee, and that link will be in the video's description. Thanks for watching. I hope that you enjoyed the video. Have a great day.